Hi everyone, this is Paresh Motiwala from Boston. If you can hear me, just leave me a quick hi in the chat room here. Hi folks, can you hear me? Just if you can respond, that'll be awesome. Okay, we'll get started. It's 11:59. Give me 30 more seconds. Cool. Hello folks, good afternoon, good morning, good evening, wherever you are. My name is Paresh Motiwala. I'll be the moderator for the day. And before I proceed any further, I just wanted to share the slides that we typically do all the time. And Edwin Sarmiento, my good friend from Ottawa, is going to be speaking today. So, the discounted price for past summit is already gone now last week. So if you are still interested, definitely go ahead and put in this code, the VG disc G0E, to get $150 discount. And you can get free access to the content by using this passcode VGSTRKG0E. Definitely do avail it. It's a lot of learning. It's like drinking from a fire hose, but you'll remember it always. Help support PASS. There's multiple ways in which you can help. If you know somebody who's writing a great product that can be of community help here to the DBAs, developers, share them. And 100 cards for any referrals leading to a community sponsor. Definitely, Catherine Allen, sponsorship sales manager, is available at this email. That is catherine.allen@pass.org. And there are so many virtual groups. Definitely avail the most learning experience by joining any or all of these if possible. I also have the pleasure of now leading the professional development virtual chapter. So I hope to see you, some of you there too. We'll be coming up with the program for the rest of the year soon. Upcoming SQL Saturdays in US and Canada are listed here. We had one in Rochester last week where I had the pleasure of doing 2 presentations. It's awesome. About 250 people or 230 people attended that. So join a local chapter. If you don't have one, start one, and we can definitely help you see the chapter. Great advantages, face-to-face networking, in-person learning is always there. Opportunities to present and share, which is so crucial for your career. And just contact CE at sqlpass.org if you'd like to start a new chapter there. If you want to volunteer, There is a My Volunteering section under your My Past profile. Definitely go ahead and register. There's so much you can do for the community. Mind you, this community is 100 times stronger than what I've seen for Oracle. So please do go ahead and volunteer. We can use every single piece of hands that is available out there. So, and without much ado, let's talk about Edwin Sarmiento. Okay, he's a Filipino Microsoft MVP data platform and a certified master from Ottawa, Canada, specializing in high availability disaster recovery and system infrastructures running on the Microsoft Server technology stack. He is very passionate about the technology, but has interest in music, professional and organizational development, leadership, and management matters when not working with databases. He lives up to his primary mission statement to help people and organizations grow and develop their full potential as God has planned for them. Without much ado, I will pass it on to Edwin. Edwin, take it away, buddy.
Good morning, good afternoon, good evening. I don't know exactly where you guys are, but it's great to be in this virtual chapter. I haven't done any virtual chapter presentations for a while. By the way, how do I share my screen?
Here it comes, buddy.
There we are. Okay, I'm going to show my main screen. Perfect. So my key area of expertise is SQL Server high availability and disaster recovery. You might be wondering, why the heck am I doing here? I do performance tuning every once in a while, and I heard Kevin Klein, past president of the Professional Association for SQL Server, once said, when he was still working for a management consulting firm back in the days, one of the things that they did was to analyze high-performing teams. They're looking at sports teams, management teams, financial teams, legal teams. And one of the things that he highlighted was the fact that the highest performing teams, the most productive, highest performing teams are teams that are into sports car racing. Now, if you've watched any sports car events, you've probably seen that, in a pit stop, there are different people in the pit stop doing specific tasks, like somebody's replacing the tires, somebody is putting gas in the car, and which is kind of interesting how we put it, because when you think about it, the person who's changing the tires as the car goes through the pit stop is really good at, replacing the tires. The guy who's putting gas on the car is very good, putting gas on the car as the car is going to the pit stop. Every single second matters, and that's why they're one of the they're the top most performing team overall. Depends on regardless of the industry, and it's very interesting to note that even though that the guy who's really good at putting tires on the car and the guy who's putting on gas in the car is also really good at understanding how the internal combustion engine works. And for me, the only reason I highlight that is because I have a degree in mechanical engineering, and it's one of my interests. But the thing is, in order for you to become a really good professional in what you do, you got to understand how the system works. And this whole session, I know it's kind of a long and winded way of introducing what operational analytics is that, in your day-to-day job, you may have an opportunity to, work on a specific aspect of SQL Server, maybe performance tuning or troubleshooting, or in my case, HA and DR. But it is very, very important for you to understand how the underlying engine works in order for you to become very, very good at what you do, plus also contribute to, how the engine works overall, especially if it's a mission-critical database. My name is Edwin, and Presh, thanks a lot for introducing. If you have any questions on this specific presentation, use the chat window or the questions tab on GoToWebinar. We'll answer those questions maybe as we go along, depending on the time, or we could answer them at the end of the presentation. You could, connect with me on social media, LinkedIn or Twitter. In fact, if you want, you could share some of the nuggets of information that you're going to learn from this presentation. Now, a bit of a warning. I kind of call myself the self-proclaimed marketing guy, even though I'm highly technical. And so what I'm going to do is I am going to start off with the quote-unquote official marketing spiel from Microsoft when they first introduced the concept behind operation analytics. Okay, so let me put on my marketing hat here for a while. Bear with me for a second. This is not going to take so long. I'll cut it really short. The official marketing spiel for operational analytics sounds like this. Okay, imagine you've got an operational database that you use for transactional workloads, your e-commerce databases, your finance databases, everything that has something to do with transactional data. And then you got a different system that is specifically for analytics. This is where you have your data marts, your data warehouses. On top of your data stores are maybe your analytics platforms, analysis services, Tableau, Power BI, dashboards, reporting KPIs, which is good. This is how it has been for the past, years. This is exactly how it looks like. There's a bit of a challenge here because these are two separate systems. They are designed differently. Your old TP systems are highly normalized because you want to optimize them for data writes, your inserts, your updates, and deletes. Whereas your analytical systems are designed for analytics, which is highly denormalized, if you think about it, where you've got multiple recurrences of the same data, duplicate data, of course. But the thing is, in order for these two systems to look alike, I'm not saying look exactly the same, but to look alike in terms of analytics, is you kind of have that ETL process right in the middle, where you're extracting data from your transactional systems on a regular basis, maybe every hour, every 2 hours, 4 hours, every day. And then you load them into your analytical systems, your data marts and your data warehouses. The challenge there, of course, is number one, in order for me to come up with, analytics, I would have to wait for the latest ETL process to run. Now, if that's every hour, that's well and good, but every hour means my operational analytics will be as good as the last hour or the previous hour that the ETL process ran. Plus, you're also looking at licensing, you're also looking at hardware, you're also looking at operational costs because that's a totally different system. Whether it's a SQL Server database that you've configured as a data warehouse, or it's an Oracle database, or anything. Additional hardware, additional operations, additional everything, right? You also have to maintain that. Enter operational analytics. Okay, operational analytics made SQL Server a platform for combining both analytical workloads and transactional workloads at the same time, removing the need for your data warehouses, your data marts, your data stores, and have your analytical systems directly query your SQL Server databases. Okay, kind of like an infomercial where you just add whatever. In this case, it's add non-clustered column store indexes, and that's what made this thing possible. Now, here's the thing, though. Okay, it's something that you really have to take note of. Operational analytics, as what Microsoft calls it, has been a term in the industry for quite a while. It's actually called HTAP, which is an acronym for hybrid transactional analytical processing. So you're combining both OLTP systems and analytical systems in one. Okay. Didn't I say that was the official marketing spiel? Let me tell you the not so official marketing spiel from consultants like me when customers ask me about what this is all about. Okay. What I tell them, and get ready for this, there is nothing new here. And this is not to belittle what Microsoft has invested in terms of research and development and engineering efforts into bringing this feature. On the contrary, I find it really, really fascinating. Those Microsoft engineers are really, really smart about how they did this. And let me take you back a couple of versions earlier to tell you exactly why I say there is really nothing new here. Let's start off with a concept of understanding index internals. For some of you who may have been working with SQL Server, I'm pretty sure you're very confident on how indexing works. Under the covers, index internals. I highly recommend that you read some of the blog posts from Kaylin Delaney about index internals. They're amazing. But understanding how SQL Server data is stored on disk will give you an understanding of how operational analytics work. Because, like I said, remember what I mentioned earlier about those high-performing teams? In order for you to become really good at what you do, you have to understand how the engine works. And operational analytics works in a way by understanding index internals. So start off with the traditional way of how SQL Server stores data in row store format. Now, like I said, this is nothing new. This is how SQL Server has stored data ever since. Like ever since. It's been there ever since. So it really is nothing new. The way SQL Server stores data is it allocates pages from disk, 8K pages, and then stores the data on those data pages. Each data page will contain rows of data from a specific table. So say, for instance, you created a table 1, for instance, without doing anything. You created a table and then you insert rows. Every single data page, 8K pages, will contain rows, and those rows contain all of the columns for that specific table. Okay, commonly known as heaps. Unstructured data, SQL Server stores them on data pages. Now, let's say, for instance, that you created a clustered index on this particular table named test table using column 1 as your index key. What SQL Server does is it starts creating a structure. It orders the data on those data pages according to the index key, in this case column 1, which means the records will now be sorted according to column 1, whether it's ascending or descending, totally up to how you create your index. Of course, it's ascending. But the data pages are now in sorted order, and the way SQL Server navigates the data structure is through the index structure. So when you run a select statement, select star from, it navigates the tree or the balance tree, for instance. Now let's look at how you would, for instance, run a very simple query. In this case, select last name, first name, phone from the member table, where first name equal to Michael. And let's assume that we have a non-clustered index based on the first name. Now keep in mind that SQL Server stores the data in sorted order. Index key. In this case, we have a non-clustered index on the first name. Now, because the select statement has the first name, SQL Server will navigate the non-clustered index key first, just to find first name equal to Michael. Now, because the only thing we have on the non-clustered index is the first name and the corresponding clustered index key value, SQL Server will still has to navigate the clustered index in order to find the last name and the phone number value. Now, the clustered index is the base table. When you create a table, when you insert records in that table, and you create a clustered index on that table, the data exists in the clustered index. That's exactly your underlying data. Of course, it's sorted according to the clustered index key. Let's visually illustrate how this how the structure works in order to satisfy this query. So SQL Server will use the non-clustered index to find a first name, found a Michael first name, and in the non-clustered index, SQL Server will use the clustered index key to navigate the clustered index and find, what else are we looking for? We're looking for the last name and the phone number. In order for you to get those records, based on the query you executed, SQL Server has to navigate the B tree. Now, this is using the traditional row store way of SQL Server storing data on disk. Now, each page contains one or more rows with all of the columns in the table. Why am I highlighting that? Well, because it's not really efficient. It's not designed for analytical workloads. When you're looking at analytical workloads reporting, you're looking at aggregation, you're looking at maybe doing a sum or an average, which means you have to read all of the columns in order for you to come up with a sum. This is where a new way of storing data was introduced in SQL Server 2012. Didn't I say this is nothing new? Introduced in SQL Server 2012 is the concept called non-clustered column store index. Okay. In SQL Server 2012, when you create a non-clustered column store index, it's as if you're creating a duplicate table. You're taking every single column and every single row on one table. You create a non-clustered column store index, and it's as if you're creating a duplicate table. It's an extra copy of the data. But there's a bit of a caveat back in 2012. When you create a non-clustered column store index back in the days, it renders the table read-only. Not really good if you're looking at transactional system, because you're supposed to be inserting records into a transactional system. I mean, think about it. If Amazon didn't take in orders just because their underlying databases could not insert records, it becomes a business issue. And this is one of the reasons why when SQL Server 2012 introduced the concept of column store indexes, a lot of customers are quite hesitant on how they adopted column store indexes. Okay, but before we really dive into how this thing works, let's look at the structure of column store indexes. And by the way, SQL Server also introduced the concept of updatable, quote, end quote, updatable clustered column store indexes. Remember the challenge when 2012 was introduced with column store indexes, were non-clustered, by the way, they render the data or the table read-only. You can't really do much. It's good for analytical systems when you're running aggregations and reporting and analytics, but not for transactional systems. The goal here is to make our databases work for both OLTP and analytical systems. And like I said, it's important for us to understand this storage structure. Recall that in a traditional row store, SQL Server will allocate data pages for the data in a specific table, sorted according to the index key. If it's a clustered index, it's sorted according to the clustered index key. If it's a non-clustered index, it's sorted according to the non-clustered index key. Now, when you create a column store index, regardless of whether it's clustered or non-clustered, okay, and I'm going to explain more in detail why I'm trying to move away from that term of clustered and non-clustered. When you create a column store index using this specific syntax, with the special column store hint on that command there, what SQL Server does is it converts the storage structure from the traditional row store into column store. Think of pivoting the row. When you pivot the row, right? Now it's in what used to be horizontal, it's now vertical. But instead of storing all of the columns for a row in a data page, what SQL Server does is it creates the concept of segments. Think of segments as data pages, but instead of having all of the columns for a row in that particular data page, segments only contain one column. Think of it this way. I've got 10 rows in a table, and I've got 5 columns for that table. A segment will only contain one column for all 10 rows. So in this case, it'll be a lot more compact. In fact, SQL Server uses a compression algorithm to achieve this so that it could store more data in a segment. And like I said, imagine you've got like 6 columns for the table named Table 1. You would have the 6 segments. And each segment will contain, depending on the data, a subset or all of the rows for that particular column, which makes it easy because now you can compress the data. Imagine when you're trying to do compression, and the way SQL Server does that, it uses several algorithms. Instead of storing 1, let's say for instance, column number 3 has a value of 1, or let's use a text value, say ABC, in the word A, or the letters ABC appear multiple times within the column, it will just use a pointer and a dictionary pointer and only store those information inside a column, making it even more compressed. And you can look at a concept of a row group where a series of segments now appear as a group within a row. Now, why is this important? We'll have a look at it later when we look at the demo. Each page contains data from a single column, making it easier for SQL Server to do a lot of compression for that specific segment. Okay, again, like I said, think of a segment as a data page, but instead of having all of the columns for a row, it will only contain one column. And that segment could contain all of the rows within that table, or maybe a subset, depending on the number of rows and the amount of data that SQL Server can fit into that segment. The way SQL Server stores data in both the row store and the column store affects how you would write data into those data stores. I mean, think about it. If you're trying to write, I'm old school, I still use pen and paper. If you're trying to write into a small notebook, it's quite different than the way you would write in a much larger notepad, for instance. So let's look at how SQL Server inserts records into a column store index. Keep in mind, all of the segments are compressed, highly compressed. So when SQL Server inserts records in a column store index, this is what happens. There is an underlying storage called Delta Store, and the Delta Store is similar in the storage structure to the B tree. It uses data pages and it stores data in row store format, but is specifically allocated for column store indexes. Now, if you're trying to insert anything below 100,000 rows, the data will land into the Delta Store. Okay, the data will land into the Delta Store. Why? It's easier. SQL Server will just insert records into data pages that are structured as B-tree structures. For anything above that, SQL Server will then create a new segment for it, compresses that row after you insert those records. Now, you also have to understand that because SQL Server will create segments, it is very processor and memory intensive. Because what SQL Server does is it will allocate the data, or rather the data store, the segment. It will allocate the segment, calculate how those rows will get allocated onto those segments, and then compresses those segments. That is why it is a very operation intensive or processor intensive operation. For deletes, this is what happens. So let's say you're trying to delete a row in a table that has column store index. What happens is, because those segments are highly compressed, it is very expensive to delete a row within a segment. I mean, think of it this way. If SQL Server will try to delete a row within a segment, SQL Server will have to decompress, uncompress, whatever it is that you want to call it. I'll call it decompress, uncompress. SQL Server will have to uncompress this segment, find a row that contains that value or that row that you're trying to delete it, compress it back. Now, keep in mind, we're just talking about one segment. Your row would contain all of the segments, right? Because your column store index will contain all of the columns subdivided into segments. So imagine SQL Server having to uncompress, delete the row, compress it back for every single segment that affects that specific row that you're trying to delete. Very, very expensive. And so what SQL Server does is it doesn't even touch the segment. What it does is it marks the delete bitmap. This is an area in the storage mechanism where SQL Server will then mark that row for deletion later on. Kind of like the ghost cleanup process where SQL Server will clean up the records asynchronously and under the covers. Okay, we understand how inserts works. We understand how deletes work. What about updates? Think of updates as a delete followed by an insert. So we're going to apply the concepts from inserting and deleting when you're trying to update a row in a column store index. So what happens is, like I said, think of an update like a delete followed by an insert. So SQL Server will mark or find that row in a particular segment that is marked for deletion, mark that in the delete bitmap, and then inserts that row or that value for that row in the Delta store. Now, what happens is that on a regular basis, SQL Server will look at the data in the Delta store and then slowly trickle that into segments. On index maintenance, SQL Server will look at the delete bitmap and then starts reorganizing data based on, hey, do I have data in the delete bitmap? If I have, I'll mark that record as well. I will delete that record as part of the index maintenance. We've looked at how column store indexes work. In 2016, SQL Server introduced the concept of updatable non-clustered column store index. So a trip down memory lane, SQL Server 2012 introduced non-clustered column store indexes that could not be updated. 2014 introduced clustered column store indexes that are updatable. And in 2016, SQL Server introduced updatable non-clustered column store index. There's a reason updatable is in double quotes and non-clustered is colored, and I'll explain why. Okay. When SQL Server 2016 introduced updatable non-clustered column store indexes, you could think of non-clustered column store indexes as non-clustered index, but instead of being stored in row store format, they're stored in column store format. So just like when you're creating non-clustered indexes, you can create a non-clustered column store index by, maybe specifying 2 or more columns. Not necessarily all columns, unlike in SQL Server 2012, or not necessarily in 2014, where you could create a clustered column store index that contains all of the columns. Here, it could be a subset of the data. Like I said, it's similar to how you would create a non-clustered index. The only difference is the storage format. Okay. Didn't I mention there's a reason why I had the updatable term in double quotes and clustered in different color? I don't want to say that Microsoft's playing a trick on us, but now that you've seen and understood how clustered column store indexes or column store indexes work, there's really no updating happening. In fact, everything's happening on the Delta store, right? When you're inserting a record, it gets inserted into the Delta store. If you're updating a record, it's happening on the Delta store plus the delete bitmap. So there really isn't any updating happening. And the ordered, and this is what really threw me off when I started looking at the data structures underneath. When you think of indexes, whether it's clustered or non-clustered, you immediately associate indexes with sorting. Remember, if you're creating a clustered index, the data in the data pages will be sorted according to the clustered index key. When you create a non-clustered index, the data in the non-clustered index will be sorted according to the non-clustered index key. Not so with Columnstore index. In fact, there is no concept of ordering in a Columnstore index. If you want it to be sorted, you would have to create a table first that is sorted according to whatever column you want it sorted, and then create a Columnstore index based on that table, which is kind of interesting because when you think about it, like I said, when you create a non-clustered index, the traditional row store, you create a non-clustered index, the table, or rather the index, is sorted according to that non-clustered index key. Again, not so with Columnstore index. So let's look at how this works. It's very interesting to talk about it. It's even more interesting to look under the covers. Think of it as, opening the trunk of a car and start looking at how things work. So let's look at a sample table. By the way, the data that I'm going to be using for the demo is from the TPCH or TPCC sample data, which I've downloaded, created into a database called SampleDB. Not so fancy, but I'm only looking at the line item table. I've got two tables called line item and line item CCIX. They're both the same. The only difference here is the name. Okay, table structures, the name of the columns, data types, everything's the same. The only difference between the two is that one has a suffix, just for me to identify which one is which. In fact, if you look at the if you look at the structure for both, they look exactly the same. Okay, so let's use, well, I'll probably just show you. Number of columns, no indexes, line item, same thing. Number of columns, the same. Data types for the columns, no indexes. Total number of rows, the same. They look exactly the same, only the name's different.
Hey, Edwin, Paresh here. There's a question. I don't know if this is a good time to ask them or.
Sure.
So what is the Columnstore index is already created? Is it possible to see the sort order without remembering or knowing the situation before?
Yes, and I'm going to show you that in the demo.
Cool. Thank you, sir.
It's actually a really good segue, a really good question to do a segue. So let's look at the underlying storage structure. Keep in mind, the line item table is a heap, no index, nothing. You run that, and when you look at how this thing looks like, you now have a number of rows. Oops. Number of rows. I'm not really good at drawing. And you got like 104,300 pages. Level 0 simply means that this is a heap. You only have leaf levels. There are no intermediate pages in order to navigate the B tree. Remember that B tree structure that we were looking at earlier. And so, like I said, if you kind of compare the two, line item CCIX and line item tables, they're both the same as far as the structure is concerned. They're both have the same number of rows, both have the same number of pages, no indexes, nothing. Okay, what I'm going to do is I am going to first create a clustered index. The reason I'm using these columns is because I'm going to use them later for analytics workloads. Now, keep in mind, this is a transactional database, but I'm going to be using them for analytic workloads. So let's create a clustered index. Now, this is no different from you creating indexes on an existing table because you're using them for reporting. Okay. The only challenge in the past was the fact that when you're creating indexes, you have to think about, oh, what queries am I going to run off of this table? Because you don't want to be creating more non-clustered indexes that would eventually impact the performance of your transactional system. So for instance, creating more non-clustered indexes would impact your inserts, updates, and deletes. It will become slower just because of the fact that an insert into the underlying table has to update the pointers for the corresponding indexes. And the more indexes that you have, the more SQL Server will have to perform more work just so it can update all of those pointers to the records that you've inserted or updated or deleted. Okay, so now let's look at the table structure. I'll run the exact same query, but this time I'll be looking at index value equal to 1, which is a clustered index. Remember, we created a clustered index based on these 1, 2, 3, 4 columns. So now my index key is a bit wide because I've got like 4 columns in my index. Let's look at how this thing now looks like. You still have the same number of rows. And this is your leaf, this is your leaf level leaf level for the index. So the navigation starts from this. Remember our animation earlier when you're running a select statement against a table, when you have clustered index, it will start off from this to find the pointer for specific records, and then we go to this level 3, and then we'll go to this, and finally here. Okay. Now, we've looked at how the line item table with a clustered index looked like. Let's create a Columnstore index on line item CCIX. Now, keep in mind, this is exactly the same as the line item table, but because line item now has a clustered index, this one does not have a clustered index, we're going to create a clustered Columnstore index for this. Both tables will now have indexes. The line item would have the clustered index. The line item CCIX will now have the clustered Columnstore index. Like I said, I really don't like the idea of calling it clustered because clustered gives me the impression that it is ordered, but when you look at the structure, the data structure, you would see that it is actually not ordered because my line item CCIX table is a heap. There is no order. And so when SQL Server creates the clustered Columnstore index, there wouldn't be any orders. Take a look at the table structure. And notice, I've got 1, 2, 3, 13 segments. Each segment has an average of 1 million rows, average, roughly. And the way SQL Server would compress the data in order for the rows to fit into this particular segment depends on the algorithm that it uses and how you would configure that. You see there are certain rows, rather segments, with only 518 rows versus those with almost 1 million rows. And like I said, that's because there are certain segments that could have duplicate rows, duplicate values. And what SQL Server does is it will create a dictionary definition for those rows and just store pointers instead of storing the exact value. Unlike with the traditional row store, SQL Server will store the exact value of the column in the data page. Now, when you look at the difference between these two, when you look at the difference between these two, you would see that line item CCIX has, as far as the data is concerned, less data consumed. Index size, 0. Versus line item when you got the index size and it was 852 megs versus 258 megs in terms of storage. Now let's look at the performance. Okay, I'm running a query against line item using this specific query, and I'm also going to run a query against the line item CCIX, I'm going to use the actual execution plan. Okay, they are the exact same query, mind you. They're the exact same query, except that the first query would be executed against a table that only has clustered index, versus the second query will be executed against a table that has a column store index. And look, you could look at the actual execution plan and the relative weight, relative cost of these two. Same value, when you think about it, the same value. When you look at the amount of time, this is the amount of time for running the query against the table with only the clustered index versus the amount of time, the amount of time it took to run the query against the table with column store index. When you look at the execution plan, 97% was spent on executing the query that was ran against the table with only a clustered index versus 3% on the table that was configured or created with column store index. Okay, so you have an idea of how the storage subsystem stores these data in terms of row store versus column store. Now, we haven't really talked about operational analytics yet, so let's look at HTAP. We're now combining column store and row store. What you've just seen from the demo is how clustered index, the traditional row store, works, and how column store works, including the queries that were executed against those two. When you look at operational analytics, or HTAP, it's simply a combination of your traditional row store plus column store. That's all it is. And so, knowing what we know about the traditional B tree and how column store works, let's combine those two when we're looking at operational analytics, or combining transactional workloads versus analytical workloads. When you do an insert, say you run an insert against a table, if you have a table with your traditional column non-clustered index plus the clustered index plus column store index, this is what SQL Server does. It will simply insert that row in the data page. It could be the last page in the index structure. Okay, it's a simple insert, but when you look at what happens in the column store, SQL Server will just insert that same row, in this case, the Delta store. Okay. When you're looking at a delete, SQL Server will navigate the B tree and look for that record and mark it for deletion. It will delete it off of that data page. But because you now have a column store index, SQL Server will first look at the Delta store. If the record is in the Delta store, SQL Server will just delete it off the Delta store, because the Delta store looks exactly, well, I don't want to say looks exactly, but it is structured like your traditional B tree row store format. Okay. Now, there is a new object called the delete buffer. If you've included or created a non-clustered column store index, the delete buffer acts like a delete bitmap, but in this case, because you're dynamically changing the data as you're performing OLTP workloads, SQL Server will then store the pointer in the delete buffer instead of the delete bitmap. Okay, so SQL Server will delete the record off of the data page. If it's in the Delta store, it will delete it off the Delta store. If it's not in the Delta store, say the record has already been in one of those segments, SQL Server, same thing as what we looked at. It will look for that record in one of the segments, get the pointer, and then store that pointer in the delete buffer, so that the next time that you do an index maintenance, SQL Server will then use that pointer in order to rearrange the records in those segments. An update, like I said, is nothing more than a delete followed by an insert. So this is exactly what's going on. SQL Server will navigate through the B tree looking for that record that it will update. The thing about the B tree or the data page or the row store format is it will just look for that data page and change the value in that data page for that column that you're trying to update. So say you're updating like 3 or 4 rows, rather 3 or 4 columns for one record. Because the record sits in a single page, only one page gets changed. On the Columnstore side of things, because an update looks like a delete followed by an insert, SQL Server will look at the delta store. If the record is in the delta store, it will do exactly what it did on that specific data page. It will just modify those records in the delta store. Now, what if it isn't in the delta store? What if it is in one of those segments? SQL Server will look at the segment, look for the pointer, and store that pointer in the delete buffer. And then it will add the new value in the delta store. Okay. Think of the delta store as the landing storage mechanism for anything that would not require a new segment when you insert, update, or delete records. What about selects? When you're doing a select statement for transactional systems, you're looking at very small subset of data. Of course, in most cases, I've seen queries where joins and all the columns are getting retrieved, but that's not what I'm trying to point out here. Like singleton lookups, for instance, the query optimizer will choose the appropriate index. So say, for instance, you're only looking at 2 or 3 rows. It would be very expensive for SQL Server to navigate the non-cluster or the column store index just to find 2 or 3 rows. So what it does is it uses the B tree, the row store format, in order to find those 2 rows. Now, if you're looking at an aggregate, so say, for instance, you want to calculate the sum of last month's sales, because it is more efficient to use the column store because you're already compressing and combining column values within segments. SQL Server will now look at the column store. The query results, keep in mind that we're now looking at both the delete buffer and the delete bitmap, a combination of those two. If, let's say, your select statements would include records that have been either deleted in the past or updated, SQL Server will exclude records in the delete bitmap and the delete buffer. And like I said, for singleton lookups, it's cheaper, more cost-effective for SQL Server to use the row store rather than the column store. For aggregations, it will use the column store. So say, for instance, you want, like I said, you want to calculate the sum of last month's sales. Because one column is used for calculating the sum of last month's sales, it'll be more cost effective for SQL Server to just use the segment of one of the segments off of the column store index. So let's look at that in action. And what I'm going to do is I am going to run a query, very simple query. First, let's start off by looking at the line item table. It has a clustered index, but no non-clustered index. Okay, I think I have that. Yeah, I'll just use this and copy everything. Oops, my bad. And the only reason I'm copying it to a new quarter window, so I want to do some comparison. So let's run some queries. This time, we're only going to be using the line item table. The line item table only has a clustered index, but no non-clustered index. So let's see. We'll run the actual execution, display the actual execution plan, and see how long it takes to run this query. And then let's put on the hat of somebody who is performing query optimization and tuning and follow the process that we would do. In this case, it took me 4191 milliseconds to run the query. 4191, and I've got a very simple table here, kind of simple, 4191, for queries that only had clustered indexes. Of course, when you look at the execution plan, it gives you that missing index hint. So let's try. And by the way, if you look at the messages tab here, it's doing a logical read of 1074249 scan count just for that table. So let's do this. Let us create a non-clustered index based on these 3 columns. Why these 3 columns? Because these are the columns that I'm using in my query. I've got my line item, or rather my ship date, my discount, and quantity. So let's create the non-clustered index based on those 3 columns. Okay. And what we're going to do is we're going to rerun the exact same query, this time with the clustered index plus the non-clustered index. So when we had the clustered index alone, it took 4191 milliseconds to run the query. This time, it took 4149 milliseconds. 4149. Wait a second. It's better. 4191 versus 4149. But when you look at the number of logical reads, you probably notice that this one had more logical reads, and that's because SQL Server has to navigate the non-clustered index as well for the query. Okay, let's proceed by creating. So let's replace the existing non-clustered index. By the way, when you look at the oh, this is not the one. When you replace the existing non-clustered index with the new definition with an included column, this was based off of the hint. When you look at the hint, it says you include the extended price column. So let's do that.
Hey, Ed.
Sure.
Just a couple of questions and a 5-minute reminder, so
sure,
you know that. Okay.
Mm-hmm.
The question was, can a table have both clustered index and a clustered column store index?
Great question. Remember what I mentioned earlier about having a clustered index in a traditional row store versus a clustered index in a column store. Okay. The thing is, you could have both, but the question is, would you want to have both?
You're defeating the purpose, right?
Exactly. Because keep in mind that column store indexes were designed for analytical workloads, and you have clustered indexes that are built for transactional workloads, which we'll look at after this demo. So here we're dropping and recreating a new index definition with an extended price included. And once this is done, we could now rerun the same query and note how long it will take for this query to run. I'm gonna open up the kind of like the table. 1205 is when we use the non-clustered index plus the included column. Now, we're making progress in terms of doing performance tuning. So why don't we do this? Instead of just leveraging on non-clustered indexes, let's use non-clustered column store indexes. Okay. We'll replace the definition of our non-clustered index with a non-clustered column store index and use those columns that we added in our definition and rerun the exact same query. Again, this is running off of the line item table, which has an existing clustered index, plus now a non-clustered column store index. We replace the non-clustered index with a non-clustered column store index. Let's rerun the exact same query. Let's rerun the exact same query and see how much improvement we got from including a non-clustered column store index. 253.
Yay.
The numbers speak for themselves, but, and there's a big but here. This is expensive. This comes at a cost. The reason I'm saying this is because you also have to balance, just like when you're creating non-clustered indexes, you have to balance the operational workload with the analytical workload, because it is more expensive to maintain non-clustered column store indexes than row store indexes for OLTP workloads. When you saw me do, the conversion, it took quite a while for SQL Server to create the non-clustered column store indexes, because keep in mind, SQL Server will have to, compress the rows in the segment or the column values to make it a segment, and it has to do a lot of these things just for you to return a query. And you're mixing transactional workloads with analytical workloads. This is where this specific recommendation comes in. You consider replacing row store non-clustered indexes with non-clustered column store indexes. And you do what I did. You run a query, tweak the index definition. Maybe you're satisfied with non-clustered index, the traditional row store, but because you're starting to have more analytical workloads, you now combine non-clustered column store with non-clustered row store indexes. The non-clustered row store indexes will take care of a transactional workload, and the non-clustered column store will take care of the analytical workloads. And there are a couple of things that you could do, like for instance, using filtered index, which will have a subset of data which is not included in the non-clustered column store index. Now, keep in mind, filtered indexes are not new. These were introduced in SQL Server 2008. Right? And the way you do this is you create a where clause when you define a non-clustered column store index, similar to how you would create a filtered index using the traditional row store. Another thing is by using what is called a compression delay. This configures how long data stays in the Delta store. Now, like I said, the Delta store would have row store based format when storing the data. Now, both approach can be used, for instance, you want to treat cold data with hot data. You can say hot data is anything that's between 2 weeks and today. So that's hot. Anything older than 2 weeks would now be moved to the column store index and converted into segments. And the way you do that with compression delay is by using the with compression underscore delay, where the value is in minutes. This is how operational analytics work. When you think about it overall, it is just about how you understand indexes underneath that makes operational analytics possible.
Cool.
Any questions apart from those that were already asked earlier?
No, I have a couple of them, so let me just ask them.
Sure.
This one is from Dwayne Emberson. I have a database that nightly has all its tables truncated and rebuilt from PostgreSQL database.
Mm-hmm.
There is no data entry against these tables. They are only reported against. What would be the impact of having these tables use clustered column store index?
What's really interesting, I haven't even talked about including in-memory OLTP or in-memory tables in the mix. In your case, because you're truncating the table anyway, and you're not keeping those data, you could leverage in-memory OLTP and then build column store indexes on top of them. The storage mechanism is different, but it'd be a lot faster when you're truncating and repopulating those tables on a nightly basis. Because when you're looking at ETL processes, you're looking at maintenance windows. You don't want the ETL process to go above and beyond your acceptable maintenance window.
So then the other one, I think the last one is what that 1M represents in the insert slide.
Great question. Approximately, and I say approximately, SQL Server will create a segment with approximately 1 million rows. depending, of course, on the size of the column, the data type, and the compression algorithm that's used. In fact, you haven't seen from the demo, you haven't seen anything that's close to 1 million row. It's almost, but not exactly. That's the maximum. Now, if a column, for instance, has 25 million rows, and SQL Server uses the compression algorithm and the data dictionary for coming up with the values, it may come up with 25 segments or maybe 5 segments, depending on how, again, the data and the column values and the data types and compression works. But the 1M there is basically the approximate value of the number of rows that SQL Server will store in a segment.
Cool. So I think that's about it. Thank you, Ed. I really appreciate that, guys. And just as a reminder, this program has been brought to you by Quest, our sponsor, without whom we cannot have these kind of programs and the raffles at the end of the presentation. So a big high five for Quest Software. And Ed, thanks for your time, my friend, and I will see you in Ottawa soon, okay?
And
If
thank
you
you
don't
very
come
much
to
for
Boston.
attending.
Cool. Thanks, folks, and have a lovely spring whenever it starts.